All right, yesterday we did a titration in the lab, either theoretical or actual in-person titration. So you're going to continue to think about and do those graphs, and we're going to talk a little bit today about sort of the quantitative aspects of acid-base titrations. So section 8.5, we are going to get into understanding what these mean. Okay, so these can often be used to determine the concentration of an unknown acid, where we reach that change of color that we saw in the lab. And there's some terms that will make more sense to you after seeing the diagrams or doing the lab. A strong acid of known concentration, the titrant, is added to a base of unknown concentration, the analyte, which is mixed with an indicator. Okay, so the analyte is the one that's down on the bottom, and the titrant is the one that you're adding. Or you could have a strong base of known concentration as the titrant, and then an unknown acid concentration as the analyte. You'll pick an indicator that works well so that it changes color to signal when you're at the end point for that particular titration. The end point is defined as that point where it changes color. When the correct indicator is chosen, the endpoint will be very close to the equivalence point. Now, what the equivalence point is defined as is when the number of moles of titrant is equal to the number of moles of analyte. And for those of you that did the lab, we kind of knew that that was going to be borderline 25 mils, because that would be when the equivalence point was, and the end point we can see by graphing it and doing some more analysis that way. So we talk about this kind of parallels with the calculations of last chapter. You can do a strong acid, strong base titration, or the titration of a weak acid by a strong base, or the titration of a weak base by a strong acid. We're going to talk about those three things. First of all, strong and strong. Take a look at what we have here. This is a way of saying 30 with two significant figures, very common to what we used in the lab, of a 0.5 molar HCl was titrated with 0.5 molar of NaOH. Okay, so this one we happen to be adding the NaOH to the HCl. Assume that the volumes are additive and the final temperature is 25 degrees. The at-home learners couldn't see this, but we had a temperature probe that was used to calibrate and continually look at, because the temperature does make a slight difference. So to take that out, our pH meters actually have temperature probes, and you guys that do come to school will get a chance to see this and even use our pH meters, probably more along the order of buffer, which is what we'll be talking about next week. All right, so it said find the initial pH of 0.5 molar HCl, and then find the pH after 15 mils of the NaOH was added, and then find the pH after 30 mils was added. So we could hypothetically predict the pHs of these amounts, and then even after 45 mils of the NaOH was added. Now remember, the net ionic equation for strong and strong is super simple. H plus OH minus gives you water. Okay, so the initial pH is calculated simply using the concentration of the HCl, because it's going to be 100% ionization, and it was a 0.5 molar concentration of HCl, The negative log of that is 0.30, very low pH as expected. All right, now it says find the pH after 15 mils of the titrant was added. So again, let your gut tell you, if I want to compare these two different things, get them to moles. The goal is the mole. Look at that. It works again. Moles of HCl initially, well, you had the 30 liters of solution, and this is the concentration of the solution, again used as a conversion factor. We've done that many times right now. So when you see that capital M, remember that can be used to convert moles to liters. All right, and that gives us 0.015 moles HCl. And then you do the same thing for NaOH, which was the same concentration, but you have a lower amount of it. So turns out we still got more HCl than we got NaOH by that factor. And this is looking at it, atom to atom, molecule to molecule. So we can write those two initial concentrations when we are doing this. And then we talk about the change. The change will be the OH, all the OH will react with the hydrogen because hydrogen is in excess. And you can see that we end up with a little bit of extra hydrogen. Because, and then all the OH is gone because it was sort of the limiting reactant, actually the limiting reactant here. And the equivalence point has not been reached yet. All right? So we'll show you data that shows that. Now, find the hydrogen ion concentration. Well, that's not too hard. You simply take the new volume, because you've added 15 more liters. Sometimes people forget that little step. And then you just go, hey, I know how many moles of the stuff I got, and I can take that and divide it by moles divided by liter will give you the concentration. So I have a 0.17 molar hydrogen ion, and you should be able to do this in your sleep right now. The negative log of 0.177 is 0.77. So that's the new pH after you've added 15 milliliters. Kind of a nifty little problem there. All right. Now the next question was, after 30 mils of NaOH was added, what do we got going on there? Well, equal moles of NaOH and HCl have reacted. 30 mils of this, 30 mils of that. All the hydrogen ions will react with all of the OH ions. You're all now in a 1-to-1 ratio. If you figured out the moles of these, they would be identical. And this is the equivalence point. pH 7 is the equivalent point for all strong acid-base titrations. This is not going to be the case with our lab, although, you know, one of them was close to that, the other one not quite as close. So the equivalence point can be figured out easily with strong acids and strong bases, because that's when the volumes are the same, which is the case after 30 milliliters. And of course, 45 milliliters, you're going to be past that equivalent point. Your moles of hydrogen initially was 0.015, and if you take a look at this, you have now added more moles of NaOH than you initially had for the acid. So that means bases now win in the race. Bases win in the race. Does that rhyme? Base race? Yes, it does. 0.023 moles. You're going to set up a similar. I don't know necessarily if you need to use an icebox for this. You could just set this up as a pretty easy little couple of subtraction problems. And these are going to wipe each other out, and then you'll have some excess OH. Not much at this point. And this, again, you might want to indicate that the equivalence point has been passed because you now have more OH, and you initially had that acid that we were titrating, remember, with the base. We're adding more and more base. So to find the pH, you're going to have to start with POH. Remember the volumes, assume they're additive right there. You do that, POH equals negative log of the 0.1, which is what you get when you do that fancy math there. So that's 1.0 for a pH. Right? That's 1 sig fig, remember. Okay, so then finding the pH, hopefully you can do this one in your head, is 13.0. Okay, that's important because just the fact that it's 13 doesn't change the fact that you're one place to the right. So that also has one significant figure, and that has one significant figure. So that's the basics of a strong acid, strong base titration. Now, your gut is telling you, I'll bet it's a little more complicated when you use the weak ones because of that whole equilibrium concept and Ka values and all that fun stuff. All right? And that is going to be true. So what does this look like as a graph? Your graph isn't going to be quite this clean, but it'll look somewhat like it. This would be the one where, of course, you started off with an acid in the bottom and you added the base. I think that was groups 1 and 3 for my third block. So what happens is you just keep adding and adding and adding, and you get those slight increases in pH. And then we noticed when we did this titration in the lab that it just skyrockets as you near the equivalence point, which can be pointed out right as 7 on this particular graph. Okay? And then you go for a while, it keeps going up and up and up, and then as you get near about 12 to 14, it starts leveling off real nice. That's a titration curve, and that's what you're going to be doing 2 of those for Friday. I think we mentioned was the due date on that. All right. So again, this is rewords this. The change in pH is less than 1.5 over the region where a ton of base was added. Okay, so it took that much before there was, and then the change is very large in the vicinity of the equivalence point. Okay, I think that those things, the graph kind of speaks for itself, but pause and write that down if you want. Okay, all right, so we'll do another one of these, a strong acid, strong base titration. So we might get interrupted in the middle, but I'm just going to use all the tape on these videos here. So you have 31.25 milliliters of this concentration was titrated with an unknown concentration of NaOH. And then it tells you when the end point was reached. All right? So this is like we talked about, where you can use it to predict this unknown NaOH acid. Find the concentration of that unknown. So we start with moles of HCl in the solution initially. Piece of cake. You just take the volume, and be careful, that's 4 sig figs right there. So it's not going to affect your final answer, but you got to make sure you write down all those numbers. And again, use the concentration, M, as a conversion, and turn that into moles, and you have that many moles of HCl initially. Now, the concentration of the NaOH titrant will be defined as the moles of NaOH, which we know to be the same. We said that that's what happens at the equivalence point. That mole amount is equal to that mole amount, and then you just put that over the total volume, and that is going to be the concentration of your NaOH. Okay? So we're going to stop right here, and we'll jump right here on titration video number 2.